Hello everyone, thank you for joining today's webinar on choosing the right magnet material for electric motor design. I'm Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs, from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platform, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all the questions at the end of the presentation. So here is our today's agenda. First, we'll go through the brief introduction about the magnets. Then we will look into the design challenges, and we will go through the simulation results using our software EMWorks 2D, and then we will conclude today's webinar. Well, motors are all around us. They are practically indispensable in almost every major industry and can be found wherever there is a mechanical movement. In the average household, you will likely find electric motors in your washing machine, microwave, refrigerator, ceiling fans, hairdryer, and the list goes on. On an even smaller scale, micromotors can be found in your most used electronics, computers and laptops. Motors use the power of magnetism to create rotational motion. Think about attracting and repelling forces and how they cause movement. Building a simple motor requires the following parts: a rotor, commutator, brushes, field magnets, and power supply. When it comes to field magnet, you can choose between several types. Broadly speaking, there are four main types of magnet. First is ceramic, which is also called as ferrite magnets. Then we have alnico magnets, samarium cobalt magnet, and neodymium NdFeB magnet. The last type is the most commonly used in traction motors for hybrid and EVs, and each has its benefits depending on your specific applications. Now let us look at its key properties as demonstrated on the right side. While both type of rare earth magnet, that are samarium cobalt and NdFeB, are extremely strong, as you can see here, samarium cobalt is more resistant to high temperature and corrosion. For this reason, they typically withstand high temperature motor applications better than neodymium. Neodymium magnets are more vulnerable to corrosion. However, this can be combated by adding a protective coating layer such as nickel or copper nickel plating. Despite neodymium's shortcomings in relation to temperature, it produces the most energy. When deciding which type to use, consider both maximum temperature required and the total cost. Alnico and ceramic magnets are much less powerful than rare earth magnets, which is samarium cobalt and neodymium magnets, but also less expensive. In addition, they exhibit stubborn resistance to demagnetization and corrosion. The maximum operating temperature for ceramic is 482 degrees Fahrenheit, but any losses can be recovered once the operating temperature is reduced. Extremely cold temperatures, however, can lead to a permanent magnetic loss of strength. Moving ahead, neodymium is the most affordable and strongest output rare earth magnet. The materials was developed in 1980s by combining neodymium, iron and boron. In the beginning, neodymium magnets were very costly to produce and also to buy. However, due to expanded mining operation and patent restrictions being loosened, these magnets type is now the most cost-effective rare earth type available. I'm talking in terms of rare earth type. Whereas samarium cobalt magnet also has strong magnetic properties, but they are more prone to break or chip when dropped or snapped together. Therefore, they should be handled and packed very carefully to prevent damages to the magnets. Samarium cobalt magnets are primarily made from an alloy of samarium cobalt and in some alloys iron. This material is extremely stable at high temperature and highly resistant to corrosion and demagnetization, as rare earth magnet samarium cobalt are perfect for application that requires extremely high temperatures, limited space, high magnetic strength, and thermal stability of magnetic output. And you can see here are some of the magnetic applications. So NdFeB are mainly used for DC motor, magnetic separator, actuators, and devices for medical use and disk drive printers, etc. Whereas for samarium cobalt, it has an application for sensors, transducers, and also for military application due to its thermal capability. And SmCo is also used in most of the generator and alternator application for speakers and other security systems. And ceramic is also used to strengthen the magnetic field and to reduce the lower cost. And ceramic magnet is also used in the electric motor to reduce its manufacturing cost, microphones, and other engineering and military applications. So moving ahead, each magnet alloy has certain qualities and that make it perfect for a given purpose. However, neodymium iron boron NdFeB is most frequently the material of choice due to its great strength and affordable price. So as you can see, the market value for the magnet in years is predicted to grow for the NdFeB magnets, whereas other magnets also grows but not as exponential growth as it has been seen in case of NdFeB magnet. Ceramic is also popular due to its moderate energy density and low cost, whereas SmCo offers the highest operating temperature of all magnetic material. However, due to its inherent qualities, its performance is constrained, whereas samarium cobalt is the last and the least utilized magnetic substance. Samarium cobalt has the second highest energy density and a very good sensitivity to high temperatures, but it's relatively high cost. And also you can look at the applications where these magnet shares the market is. So you can see in the past, from 2013, you can see the demand for magnet in the automotive industry has increased faster than the electronics and other energy conversions. Next, so when choosing a magnet material, it is important to consider the following key questions. First, the expected design life of the equipment where the magnet is fitted. As permanent magnets, neodymium magnets perform at their peak every 100 years if maintained at optimum conditions. A magnet's lifespan can be shortened by two factors. First is heat. Magnets lose magnetism if their temperature exceeds the maximum operating temperature, which is 80 degrees Celsius for N42 grade neodymium magnets. Similarly, samarium cobalt magnets are not as strong as neodymium magnets, but they operate at temperatures as high as 350 degrees Celsius. Second thing is corrosion. The magnet will rust if the plating on it is damaged and waters get inside, which resulting in deteriorated performance. Magnets made with samarium, cobalt, and ferrite resist corrosion but are not as strong as neodymium magnets. Next is the shape and size of magnets, or what does the magnet have to hold, lift, or attract? Well, basically the pole of a magnet is its strongest part, so it doesn't matter how small and what the shape of the magnet is, it will always have two poles. Next we have maximum operating temperature, so that we have already seen in the previous slide. Then comes the resistance to demagnetization, and the magnetic strength required. So well, many of us might think that does stacking magnets make them stronger? Because in most of the interior permanent magnet design, we try to stack the magnet into different angles or over to each other in layers. So well, stacking multiple magnets together can make them stronger. The combined strength of the magnets, the same size or smaller, will be virtually equal to the strength of a single magnet. However, it is impossible for a magnet to become stronger if it has been fully magnetized. By stacking magnets together, the strength of the stack increases until its diameter equal to its length. Any further added after this point will give only a marginal performance boost. Next, we have resistance to corrosion. Yes, like iron, neodymium magnets also tends to rust if it's left unprotected. Nickel copper nickel, which is NiCuNi, is a 3-layer plating most neodymium magnets use to prevent corrosion. For many years, corrosion protection has been provided by these specific plating combinations. And the last criteria is the cost and the budget of the project. Moving ahead, let's look at the design challenges for any electric motor design. So designing an electric machine is a challenging task as its electromagnetic, thermal and mechanical performance are coupled and need to be taken into consideration together at the same time. Based on the design constraints and other user demands, the motor designer has many choices and criteria to take care of. So estimating these parameters and losses which generate heat in the motor are one of the major challenges while designing the motor. Another characteristic of the motor is the high speed operation, that is during the flux weakening mode, and also to obtain its efficiency plot at different torque and speed. So in our today's webinar, we will be using a surface mounted permanent magnet motor design, and we will be using 4 different magnets: ceramic, alnico, NdFeB and samarium cobalt, to evaluate the performance, and then we'll compare the performance at no load and on load conditions. So to make this design process simple and easier, AIMWorks has various motor solutions. So the first, we have Motor Wizard tool. It is a template based motor design software that allows users to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic and transient solvers equipped with integrated analytical and finite element based solvers. Second, we have the AIMWorks 2D tool. It is a 2D electromagnetic simulation software that uses the finite element to solve magnetic, electric and transient problems. AIMWorks 2D allows you to study the effects of the geometric or simulation parameters changes on the design. It also allows to couple a transient magnetic study to mechanical motion and thermal. Third, we have EMS tool. It enables user to do both electric and magnetic simulations using the complete 3D geometry. EMS is a true multiphysics software that enables user to couple the magnetic and electric design to circuit, motion, thermal and structural analysis on the same model in a hassle-free integrated environment. So here are the design specifications. We will be using 12 slots with 8 pull combination, having a rotor position as inner rotor design. The base speed for this design is set at 1000 rpm. We are going to supply a 25 ampere current to each phases, and our outer stack diameter is 74 mm and the stack length is 60 mm. We have used M19 grade steel for all the 4 combinations which we are going to simulate using NdFeB, which is N42 magnet, samarium cobalt with S3214 and alnico and ceramic. And for the conductors we have used the copper material. To begin the performance analysis in AIMWorks 2D software, the first step is to set the material. We have a wide range of material library where users can choose the materials for the motor parts, and then to set the boundary conditions where we need to assign the outer, we need to assign as air region, and then we have a force where we need to select all the parts of the motor which is responsible for a force and torque generation, which is nothing but moving parts we need to select over here. And then we need to set the mesh, and you can also use a mesh control to define the mesh size, whether you want finer or coarser mesh. And then the last step is to set the winding parameters, where you can play with its amplitude, its frequency, its offset, and also if a user wants, you can import your own waveform for the current excitation. So to begin with, let's look at its cogging torque performance. So as you can see, the least cogging torque obtained is for the ceramic magnet. So having a lower cogging torque pulsation doesn't guarantee a higher torque generation. Therefore, the highest obtained cogging torque pulsation is in the case of NdFeB magnet, and the lowest is for the ceramic. We have also plotted its average. So as you can see, the highest is for the NdFeB, then comes the samarium cobalt, then the SmCo, and the least is for the ceramic. It's interesting to see that the SmCo and ceramic performance is almost the same in terms of cogging torque generation. Moving ahead, the back EMF. Back EMF is nothing but the induced voltage at no load when rotated at its base speed, and you can see as the magnet strengths keep on reducing, the overall back EMF generated is also reducing. The highest voltage is obtained in case of NdFeB, and the lowest is again obtained as expected from the ceramic magnet. Moving ahead, we have no load flux linkage. So a similar pattern has been observed in case of no load flux linkage also. Highest still holds for NdFeB, and the flux linkage is close to sinusoidal, and it has a flat top due to its magnet shaping, which is a surface mounted magnet type. And we can also see its average, it's as reduces from NdFeB to ceramic magnet. Moving ahead, we can see the input current. So we have excited 25 amperes, and we can see the current density on the right hand side plot. And it's very interesting to see the applied current density, which is one of the important parameter, as the coils are the source of heat generation, and it's very important to design the plot current density appropriately to have a proper heat dissipation. If it is a totally enclosed fan cooled motor, the nominal range for the current density is close to 5 to 8 ampere per millimeter square. Moving ahead, we have the electromagnetic load torque. While exciting a 25 ampere current, you can see the highest torque is achieved by the NdFeB magnet, and then for the samarium, and then SmCo, and followed by the ceramic magnets. In short term, I can see the torque density of the motor keeps on reducing by using a lower range magnet, but at the end it depends what kind of performance output is required from the motor. Next, we can also look at its magnetic flux density plot. So for the NdFeB, the saturation is happening inside the stator tooth, which is around 1.68 Tesla, whereas in case of samarium cobalt, the highest magnetic flux density is 1.47 Tesla. For SmCo, it's around 0.88 Tesla, and finally for ceramic, the peak magnetic flux density is just around 0.53 Tesla. So to compare all four topologies, keeping the base speed same, hence the input current is same and the volume same for all the four topology, we can observe the effect of magnet and how it affect in its torque generation capability. So the highest average torque was obtained in case of NdFeB, which leads to highest torque density, which is around 25 kilonewton meter per meter cube, and going towards the trend, the least obtained was for ceramic, having a torque density of just 4.72 kilonewton meter per meter cube. Let's move on to the demonstration part, where we'll be showing you AIMWorks 2D software. Well, so once we are in SolidWorks platform, we need to use the SolidWorks CAD features tool to design our stator core the coils, rotor core and the magnets. Once we have done with the CAD modeling of our motor design, we need to launch our EMWorks 2D software. Here, to begin the analysis, first we need to set the materials. So for materials we have rotor core as M19, rotor magnet as the first case we are simulating is the NdFeB, where we have used N42 magnets for all the magnets. The stator core as M19 and the stator is coils are used using copper material. Once we set the material, we set the air region around our motor, which we are going to simulate, and the next step is the force and torque calculation. So here we have selected all the rotor parts and the magnet for the torque computation. You can also choose between the force and the torque computation for the selected faces. Next step is to define the mesh. Here we can see the mesh generated for the motor. Here we go. Next step is to set the windings. Here we set the windings for all the three phases as shown here. You can also look at its direction of the current flow. Once we are done with the setup, we need to go and click on the right part of the study and run the analysis. Once the simulation is finished, we can click on the results and look at its results. To begin with, EMWorks 2D provide results in the tabular form, and where you can see the waveforms, and also in the form of plots. So for first, let's look at its flux linkage. So we'll add all the three phases of our winding, and we'll add to our parameters and then plot preview. So here is the flux linkage of the model. Then we can also look at its torque. We can click, add to the parameter and plot the preview, and here you can see the electromagnetic torque. Similarly, you can also see a lot of other parameters as shown here: the resistance, winding losses, flux linkage, induced voltage, inductance and many more. You can also click on the magnetic flux density and click on the show option. Here we have the magnetic flux density for the machine. Similarly, we can see its current density, vector potentials and loss density and many more. Moving back to the presentation. So in today's webinar, different topologies of surface mounted permanent magnet motors were simulated, and its electromagnetic and thermal performance was obtained using EMWorks 2D software. And we observed that the motor with NdFeB type magnet yielded the highest torque density, and then the samarium cobalt, and then comes the alnico, and the lowest torque density was achieved with a ceramic type magnet. However, in a nutshell, if I say, the selection of magnet type or the topology of a motor, whether it's permanent magnet motor, induction motor, switch reluctance motor, synchronous reluctance motor, it's completely a trade-off between what are the constraints and what are the performance requirement from the end product. So here are the references for today's webinar. Thank you so much for attending today's webinar. See you in the next webinar. Thank you.